All right, so today we're starting new stuff. Today is some of the stuff we're going to be doing, it'll make a lot more sense as we go on in that we're going to start doing comparisons, but we're going to use all the information we've learned so far. So what I mean by comparisons is, for example, we can compare two products and they both make claims. We can compare them against each other. We can compare probabilities to each other and so on. So I'm going to start with a really simple one, okay? So let's say free throws are always a great one when we're doing probabilities, because today we're doing tests on P, next day we're going to do tests on mu. So let's say right now, we'll keep it really simple, that Misky's trying to determine if she's a better free throw shooter in the daytime or in the evening. You know, because she shoots lots of free throws. She shoots thousands of free throws a day, right? But you're saying, you know, am I better at night? Am I worse at night? You know, depending. So how would you do this? Well, obviously you'd go out and you'd shoot a whole bunch of free throws in the day, and then shoot a whole bunch of free throws in the evening, and you'd compare those. But the thing is that would you expect, if let's just make it simple, you shot 100 free throws in the day, you shot 100 free throws in the evening. Are you expecting to make exactly the same?
No.
If I flip a fair coin 100 times, count the tails, and then I do it again 100 times, am I going to get exactly the same amount of tails? No. I mean, the probability of that happening is microscopic. So we wouldn't expect the same results, but really the question is, if there's no difference in the results in general, if there really is no difference in the ability, then the numbers are probably close together, aren't they? And if they were really far apart, that would make us suspicious. If you flipped one coin and got a certain number of tails, and flipped a second coin and got a very different number of tails, you might suspect that those coins are not equally weighted. But if those coins were identical in every way, you're still not going to get exactly the same results. Why? Because it starts over each time, right? The coin isn't keeping track. There's no computer chip in the coin that says how many heads or something. So we're going to do a comparison of probabilities, and there's a simple way of doing the formula. So first of all, all right, so here's the situation. So Misky wants to determine, so we have to have a reason. If there is a difference in her free throw shooting in the day versus the evening, okay? Now we haven't collected any sample yet, okay? We haven't collected any sample. So we're trying to determine if there's a difference. So we're trying to determine if the probability of the daytime is equal to the probability of the evening, or it is not. You agree? Now, we write it a little differently, though. So at first I'd say, well, why don't we call P day and P evening? So I'll say probability day equal to probability evening versus probability day not equal to probability evening. Does that sound like a good start? Just trying to determine if there's actually a difference or not. Now, what would we always start? We'd start by assuming there's no difference, and then we'd let the evidence tell us otherwise. The evidence would be your actual gone out free throw shooting, okay? Now, everything I said is correct, but I can't do it exactly this way, because if I'm doing a test on probability, I actually need a value. How do you get a value? Where's the value come from? Rather than saying equal, the value comes by taking the difference. Oh, so if they're equal, then what's the difference? If two things are equal, then what is the difference?
There's no difference.
There's a number I'm looking for.
Zero.
Zero. Yeah, that wasn't exactly something that you should have been laboring over. If they're equal, then the difference is zero. If they're not equal, then the difference is?
Anything other than zero.
Yeah, not zero. I actually need a number here. Another way of thinking about this, what if Misky believes that she's about 10% better at night than she is in the daytime? Then we'd be saying the difference is 0.1. Does that make sense? Or if she's saying, you know, I believe that I'm twice as good at night, whatever. If there was an actual value that you thought it was, then we'd set it up as that difference. So when I'm trying to determine equal or not equal, we actually say, so the difference is 0 or the difference is not 0, because I need the 0. This is going to show up in the actual calculation. Again, because she could assume that the difference is some number, you know, maybe 10% difference. A simple example for those of you who follow sports. Any sport, do teams typically play better at home or on the road? Yeah, what do we call that in most sports?
Home field advantage.
Home field or home court advantage, yeah. Oh, okay. Why? Because most teams, not all teams, most teams have better success when they're playing at home. So if we're talking about points per game or something, we say, well, the points per game on the road versus points per game at home, we don't expect the difference to be 0, do we? We expect it to actually be a significant difference. Right? Does that make sense? Oh, okay. In this case, we're trying to determine if there's a difference or not. That means the number we're looking at is 0, but the number could be something else. So the next thing we do, okay, when Misty goes out and shoots her whole bunch of free throws in the day and she shoots her whole bunch of free throws in the evening, there's an overall percentage of free throws she made. All the ones she attempted, all the ones she made. We call this a pooled probability. This is not complicated, but I'm going to show you, because when we actually do our calculations, okay, we use the pooled probability and as opposed to the individuals. So let's say she went out in general, all right, in the daytime, in the evening. She had N1 attempts and X1 successes. Obviously, we're going to consider a made basket a success, not a missed basket. Okay? And in the evening, she went out and made N2 attempts, whatever that number is, and had X2 successes. All right? So what is her daytime probability? Her daytime probability, we'll call P, the measured daytime probability would simply be X1 over N1. We know how that works, right? And her measure, that's what the hat is. That's not the hypothesized value, that's what we actually observe. This would be X2 over N2. So if she went out and shot 100 free throws and made 80, that's 80 over 100. Piece of cake. Overall, how many free throws did she shoot altogether? N1 plus N2. Agreed? How many free throws did she make?
X1 plus X2.
So her pooled probability, which we affectionately call P bar. We have a P, we have a P hat, we have a P bar. Oh my gosh. Well, when we talk about P, we're talking about the population. We don't know what that is, so we go out and we do a sample. The sample is always the P hat. P bar is all together. So it's kind of like I'm putting this one together with this one. Now, you don't add the probabilities. So Misty made 75% of her free throws in the daytime. She made 80% at night. That means she made 155% of her free throws. Wait a minute. That's not how it works, does it? You got 80% on your first exam. You got 90% on your second. So you have 170% in the course. Wait a minute. You don't add percentages. You kind of average them, don't you? Oh. So can I say I got 100% on a quiz and 50% on a test? My average is 75%. But if the test is worth more, you don't, that's called a weighted average. In other words, it's a pooled probability. What do? You take your total amount of points attempted, you take your total amount of points achieved, and you take the quotient. Agreed? That way, if you had different point values for things, it doesn't matter. N1 and N2 might not be the same number. Oh, I can't simply average. What if she only shot 10 in the day and 1,000 at night? I can't average the percentages, can I? But the overall percentage is what? You just said it. X1 plus X2 over N1 plus N2. Now, in a perfect world, I would love it if N1 and N2 was the same number. If you shot 100 in the day, I think 100 at night is perfect. Does that seem reasonable? But maybe you don't have the opportunity to have exactly the same because you're observing something. You're observing something that you don't have any control over, perhaps. I mean, it'd be great if they were the same, but they don't have to be the same. So this is overall what she did. So therefore, what would Q hat be? Just like always, just 1 minus this. just 1 minus. That's all you got to do. Okay? We know how that works. Now, variances do not average. Variances you actually add. And the variance, you remember, if it's a probability, right, was always what? Oops, sorry. In probability, like think confidence interval, you went P, Q over N under the root, and you multiplied it by the appropriate Z. But that's the variant, or excuse me, the standard deviation we used with the probabilities. Well, before what we did was, we said something like this. Miski claims to be an 80% free throw shooter. So what we did was we took her attempts, subtract the claim to 80%. So maybe she makes 75, this was the 80, and then we divided it by what? This PQ over N, the hypothesized P, right? So she claimed to be an 80% free throw shooter. We said, okay, we'll assume you're 80%. So that'd be 0.8, that'd be 0.8, that'd be 0.2, and we divide by the number. That was what we observed. So we said, we will believe you're 80% and we will let the evidence tell us otherwise. Remember, we always start with the hypothesized value being the truth, and then we look at things. The difference is I'm doing 2 sets of things. So the formula that we're going to use in this case is not the same because I'm comparing things. We're not trying to say the claim she makes, is it true or false? This is a completely different animal. She's saying, am I the same in the day or versus the evening? So is my difference 0 or is it not 0? So this is the individual. You're testing one thing. Now I have 2 things and I'm comparing them. So a comparison is a bit different. So what we're going to use, and by the way, because this is a test on P, we always use Z. Our calculated Z value will be, okay, the observed difference what we actually see as a difference. By the way, even if she was exactly the same in the day as she is at night, is it still possible we would see a difference? Remember, if I take a coin and flip it 100 times, and now I take the same coin and flip it 100 times again, am I going to get the exact same outcome? Probably not. Okay? Do you agree with that? Probably not. So, and then we're going to subtract the hypothesized difference, which in this case would be 0. So the vast majority of the time you're doing a comparison, majority of the time, this is going to be the number 0. The exception would be if Miski believes she's actually, let's say, 10% better in the daytime than at night, then we'd be using 0.1, because that's the hypothesized. Does everybody understand that? Most of the time it's going to be a 0, because most of the time you're just trying to determine, is there a difference? Not is my difference a certain amount. Okay, that's my numerator. My denominator, by the way, this is easy because just those 2 numbers right there. Over, now there's 2 different variances. There's the variance from the daytime and the variance from the evening. But what we're going to do is not use the specific values from the day or the evening. We're going to use the pooled value. This is a little confusing in this way. I'm going to use P hat Q hat over N1. I'm going to use the pooled probability. Because again, what's the hypothesis?
P bar or P hat?
I'm sorry, bar. Sorry, I said hat, but yeah, bar.
Just wanna make sure. Thank you.
We're assuming there's no difference in day or night. So what we're assuming is that if there's no difference, then we're going to take all the free throws you shot day and evening. And we're going to make that our observation. Okay? And if there's not a huge difference, it won't actually make it any deal. But if there is a big difference, we will see it. And then we're going to add to that the variance from the evening session. So this feels like a complicated formula. All of the numbers are easy. But the difference is I add variances because there's literally 2 different experiments taking place at the same time. There's her daytime performance, there's her evening performance, and I add the 2 variances together, and then the denominator is the square root. So in other words, it's still the standard deviation, but that's the daytime variance, that's the evening variance. Variances always get added together. Now I take the square root. You notice it's not the square root of this plus the square root of this. All of it is under the square root. So that's a common error that people make. Oh, so when I'm doing this on my calculator, square root key, parentheses, okay? So when all of this is said and done, if this value is too big, obviously, then we'd say, nope, it's not the case. There is definitely a difference or not. This is how we compare probabilities, and we're going to do a whole bunch of examples today of this. So this is the formula we're going to end up using. It seems fairly complicated, but once you do a couple problems, you realize, oh, it's just I'm throwing a couple fractions into a square root and hitting my calculator button, which means you got to trust that calculator. So we're going to have Miski go out and shoot free throws. Excuse me. So now, let's see what we actually observed. So we've got our setup. So now we want to test, since this is probably not life and death, let's test at the alpha equal what level if it's probably not life and death?
93.
Probably,
Or 5%.
yeah, probably the 5%, the 0.5 level. Again, we're not testing a pharmaceutical that, we're determining that it will save your life or not. Really, really, really serious stuff is usually 1%. Everything else is usually 5%. And by the way, in real life, literally those are the only two numbers people ever really use. So, is this a one-tailed test or a two-tailed test?
Should be 2.
Two-tailed. It's equal or it's not. So we're going to reject in the extremes in either direction. So here's the thing. Miski is trying to determine if there's a difference. If there is a difference, the numbers have to be really different. But do you know ahead of time if it's day or night that's better? No. So it doesn't matter. If the day is way better, we're going to get a number that big. If the night is way better, we're going to get a number that big because of the order we subtracted. This is kind of like saying, is the scale accurate or does not? It doesn't matter which direction it goes. If it goes too far in one direction, we'd say the scale is not accurate. It's that same kind of logic. So we will reject the null hypothesis when? It's a two-tailed test, so I have two tails of 0.25. We should know that number by now. If it's greater than, well, if you don't have it memorized, look at your table, put your values. No, that would be a 5% tail. There are no 5% tails.
1.96.
Why 1.96? Because I have 2.5% tail. Yeah, 1.96 or less than. If it's a one-tailed test at 5%, then it's the 1.645. But two-tailed means I have 2.5 in each tail. Okay? So I've drawn my lines in the sand, right? I'm going to reject here. I'm going to reject here. Meaning I'm only going to reject for extreme differences. Okay? Again, the analogy I'll use, if I take a fair coin and I flip it 100 times, then I flip it 100 times again, I do not expect to get the same outcome. But I do expect the outcomes aren't going to be very far apart. Agreed? Because if they were very far apart, that would be just odd. But if I have two different coins and I'm trying to determine if they have the same weight balance, now I'm not necessarily expecting the same outcome. So those outcomes really could be very far apart. Okay? You with me so far? So, Misty went out. So in the daytime, she went out and she shot exactly 100 free throws and she made 75. In the evening, she went out and she shot 150 free throws and she made, let's say, 125 of them. Okay? So now we want to determine, is there a difference? Or are those numbers closer together that we say no? We can't say there's a difference. I just saw an interesting statistic yesterday. And I pay attention to interesting statistics in sports. All right, how many watch football? Or you've been a football fan for a while. Historically, when you're watching a football game, there's two types of fields. There's a grass field and there's artificial turf. And historically, by the way, if you've ever played football, you want to play on a grass field. Why don't you want to play on artificial turf?
It's like playing on top of cement.
Yeah,
It's like carpet.
in the old days, they literally put it on top of, it's like playing on top of cement. It looks beautiful on television, but players hate it because when you get tackled, you want to get tackled on this floor? No, you want to get tackled on grass. But one of the things about artificial turf was, historically, it was like playing on cement. Now it's gotten better over the years. Yeah, the rug burns are still there, but they've made it a little bit better. But over the years, historically, people have always believed that when it comes to things like injuries, way more injuries on artificial turf because of the fact that there are seams in the turf sometimes, and just how many have heard that in your life? You know, there's way more injuries. There was a statistic that the NFL just reported yesterday. Said in terms of injuries, there is no difference. Did anybody see that article?
Yeah, I read
I was, to be honest, I was shocked. I had absolute belief that there was a huge difference in the injury rate on turf versus grass. And it said the NFL came out statistically, basically they just did this exact test. It's a test on probabilities of differences. They did the test we're doing right now, and they said there is no difference. Does that mean it's exactly the same? No, it means the difference was not significant. In other words, the difference didn't fall here or here. Yet we all suspected that artificial turf was way more dangerous. Is it more dangerous? Probably, but is it more dangerous enough that we can make that conclusion? No. In other words, using correct statistics, it wasn't dangerous enough. So we're saying, you know, they're essentially no difference. Now again, that totally surprised me. Like, I never saw that one coming. But the fact that they used proper statistics to get that conclusion, I mean, I trust the answer. I'm surprised by the answer, you know? So, you know, sometimes we don't know what's coming. So, we have all the information right here. So let's put things together. So, first of all, what is my, excuse me, what is my measured probability of daytime? That's 75 over 100. My measured probability of the evening, that's 125 over 150. Those numbers go in the numerator. The difference of those are going to be going in the numerator. Now, what is my pooled probability? This is neither day nor evening. Altogether, how many free throws did Miski shoot? Altogether?
So 250.
She shot 250. Altogether, how many did she make? 200. You can leave every one of these as a fraction. In fact, most of the time you probably will, simply because your denominators may not be this friendly. Do you agree? You know, if my denominator is 237, no, don't do a decimal approximation and then enter that in. That's overkill. Plus, that you risk rounding errors. Is this a nice number right here? What is this?
0.8.
Yeah, 0.8 exactly. Oh, okay. Therefore, what is Q hat? 0.2. That's very nice. That definitely makes my calculations a little bit simpler. I would rather enter a terminating decimal than a fraction, because the fraction is just simply more buttons. It's not going to give you a different answer. Sometimes it's just easier to enter. So now, our Z star is, and I'll put it in parentheses, the measured difference. This number minus this number, okay? Oops, sorry. I want to leave those as fractions because the second one doesn't reduce. So 75 over 100 minus 125 over 50. What is my hypothesized difference? Which I said is usually going to be the case. What's the hypothesized difference?
0.
0. Actually, physically write the 0 because in actuality it is not always 0. It's most of the time 0. So the formula is measured difference minus hypothesized difference. And now what's my denominator? It's the square root of P hat Q hat
P bar?
or I keep saying that, don't I? Sorry. P bar, Q bar, thank you. Over the different ends. So over 100 and over 150. When you're entering this into your calculator, you need parentheses on top, and after you hit the square root, you need parentheses on the bottom. But you can do this times this divided by this, plus this times this divided by this. That does not require parentheses. The total of that requires parentheses to make sure you're putting all of it inside the root. So when you're entering, the parentheses I'm writing here, are they necessary when I enter the calculator? The parentheses I have around the decimals, are they necessary when I enter into the calculator? No, you never have to use parentheses when you multiply. So why am I putting them? Because otherwise I'd be writing this. And that is really hard to read, isn't it? You put parentheses around them to make it easier to read. You don't use parentheses when you're entering in your calculator because you're doing a product. You definitely don't need parentheses. That's overkill. But if I don't put parentheses around it, when you're multiplying decimal values, I actually have many students do this. I don't know where they learned it, but I have many students in higher level classes that will do their multiplications in the same place that the decimal goes, which makes it an absolute impossibility to interpret what they mean. Never do this. But if I wrote that, isn't that some kind of weird date or something? Right? This makes no sense mathematically because I have decimal and I have multiplication written the same way. That's bad. That's not correct. But I have many students who actually do this. And I don't know what that you're trying to say there. Well, no, don't use that. Use parentheses because you already have a dot in there. So let's all do this. This is not complicated. Just take your time and see if we all get the same answer. That's always a really cool thing. Now tell me when you get a number. Does anybody have a number yet?
Negative 1.61.
Same thing? Does anybody else get negative 1.61?
Great.
Yeah, I got the same thing. But I don't trust myself, I trust you. Yeah. This is why you guys, you all have to do this. You gotta know if you're entering things in the right order, otherwise, this is the answer, but I don't know what this value is, so I have to correctly put it in my calculator. So it's negative 1.61. That's a pretty big negative z-score, isn't it? What's the problem?
Not big enough.
It's not quite in the shark-infested lava, is it? You ran full speed and you put the brakes on before you went out the door into the lava. That is a very big negative z-score. But is it big enough to reject? No, therefore, what is our conclusion? Reject or fail to reject, first of all? Fail to reject. By the way, that tells me what I'm going to do with the hypothesis. That's not yet the conclusion, right? Now what are you going to do? Now you're going to hold your press conference. You're going to tell the world what all this means. Can you say unequivocally that Miski is exactly the same in the day or the evening? That's a pretty big difference. But it wasn't big enough. So instead of saying she's the same, what are you probably going to say? There's not enough evidence to conclude what? In words, what is the alternative hypothesis?
That the difference between her day shooting and her evening shooting is 0?
No, the
Oh, it's
alternative.
not 0, yeah.
So in other words, there's a significant difference. The null hypothesis is there's no difference. To say there's a tiny difference, no. That's like flipping the coin 100 times and getting 50 tails, and then the next time getting 51. Aha, it's the same coin. You're not going to get the same number. I flipped it, it got 40 heads, and then the next time I got 80 heads. No, that would be significant. The alternative hypothesis, there's a significant difference in day and evening. That's what we're trying to figure out. There's not enough evidence to conclude that there is a difference in day and evening. That doesn't mean we believe she's exactly the same. There's just not enough evidence to say that there's a difference. That's all it is. So in other words, not guilty, but we're not saying innocent. We're just saying there's not enough evidence to prove you're guilty. Think of it that way. To conclude, there is a difference. It's very close, by the way. And here's how close it is. You know, when she was shooting in the evening, she had a couple just roll around the rim for a split second and then they fell out. Couple of them. You know, you ever seen those where they literally going in and they roll back out? She had too much backspin. She gets those two baskets, we probably are rejecting the null hypothesis. No, it's close, but it's not close enough. Now, p-value. By the way, a lot of us are forgetting this. You know, I'm doing all this experiment and I come out and announce to the world I failed to reject the null hypothesis, and then I leave and you're saying, so, yeah, is she better in the day or night or what? The average human isn't going to understand what that means in terms of conclusions. Right? So we actually have to, in words, state, this is the conclusion. I'm either going to reject or fail to reject. Had I rejected the null, then we'd say, no, there is definitely a difference in day and evening. Okay? But we were not there. So let's calculate the p-value. Now, because it's a two-tailed test, remember the p-value, I say, what's the probability of a result this extreme or more in either direction if the null hypothesis is true? See, would you say this is kind of an extreme result if she actually is exactly the same? Yeah, that's not quite extreme enough, but that's a fairly extreme result. So how reasonable is this result if she really doesn't have a difference? If the null is true, how reasonable is being 1.6 standard deviations from the mean in either direction? So the p-value is 2 times the probability of z being this extreme or more. So smaller than negative 1.61. Now we like this because I can look it up in the table easily. So let's find the value. So go to your table. Negative 161, what's the number you see?
0.0537.
And what is this value? Excuse me. This is 1074. This, I like p-value personally, because I think p-value is one of the easiest ways to understand what the heck just happened. If Miski is truly the same in the day and evening, if there really truly is no difference in her performance in the day or evening. By the way, this was 75%, this is 83 and a third percent. That's a fairly big gap, but is it big enough? If there's no difference in her skill day and evening, then we can expect results this extreme or more about what? About 10% of the time. That's not outrageous, it's not big, is it? Now remember, if the p-value is smaller than alpha, then you rejected it. The alpha was 0.5, our p-value was 0.1. So it's definitely bigger than alpha, but it's still kind of close, isn't it? The closer this got to negative 1.96, the closer we were to rejection. Had this been more negative than 1.96, our p-value would have been smaller than 0.5, and we would have rejected. Does that make sense? So, here's an example where it makes perfect sense to pool her probabilities because it's the same person shooting, the same basketball, just 2 sessions. So now, this is really the big deal. So, we're not worried about Miski's day and evening performance anymore. Oh, no, no, no. Now it's on. It's Miski versus Dylan. Okay, this is the real question. Miski wants to determine if she is a better free throw shooter than Dylan. So you guys see? I was comparing Miski to Miski the first time. Now I'm comparing Miski to Dylan. Now, how would we do this? Well, each of you are going to go out and shoot 1 free throw, and if one of you makes it and one of you misses it, then it's obvious. Is that a good way of doing anything? Probably not. I'm going to flip a coin 1 time. If it lands tails, that means it's always going to land tails. I don't think it works that way. So what are we going to do? We're going to have Miski go out and shoot a whole bunch of free throws. We're going to have Dylan go out and shoot a whole bunch of free throws. Do they have to do it at the same time? No. But we need to collect 2 sets of data. Now, here's how it works. She's trying to determine if she's better, so what should our null hypothesis be? She's not better, she's the same. By the way, could she potentially be worse? Yeah, we'll throw that in, but she thinks she's better, but how much better do you have to be before you can say you're better? Statistically significant. You gotta be in a tail, don't you? Okay, so we start by assuming she's not better, and we've never said this before, let the evidence show us otherwise. Does that sound familiar? So we're now gonna do probability, excuse me, Miskey minus probability Dylan, probability. Now, she's trying to show that she's better. That's a strict inequality. That has to be the alternative. Being better means the difference is bigger than 0. Now, in most of the textbooks, by the way, most of the textbooks will say, well, she's either the same or she's better. Well, is it possible that Dylan's better? Isn't that a possibility? So that's why I'm a big fan of doing this. Not being better means she's the same or worse. But you're saying, but worse isn't a possibility. Well, yeah, it is. In sports, what do we call that when the worst team wins? We call it an upset. And that, of course, never has happened in human history, has it? Or does that happen on a regular basis? Yeah. I pay attention to things like point spreads. I don't bet on games, but I just pay attention. One team is a heavy favorite, but the other team sometimes wins. So in other words, we're saying this, or they're not better. Well, not better might be worse. And sometimes that actually does happen. Oh, okay. So why is this important? Because we've accounted for everything. These are complements. So we're going to start by making the assumption. So mathematically speaking, the mathematics is we're going to start by assuming there's no difference. The less than is only in an extreme case, but we're going to assume there's no difference in their free throw shooting skill. And you've got to be way better before we say you're a better free throw shooter. Agreed? So if we start with the assumption that there's no difference, then it's Miskey when she shot day, when she shot evening, we started with the assumption there's no difference. So what did we do? We pooled the probabilities. This might seem a little bit strange, but if we're assuming there's no difference between their skill, it's as if Miskey shot both times, or it's as if Dylan shot both times. So we still pool the probabilities. Because if we're starting with an assumption that there's no difference, it literally means it's like the same person did all the shooting. Because we're starting by assuming there's no difference. Does that make sense? So we still pool the probabilities in the same way. So we're going to do exactly the same problem. In fact, this is important because, Missy's already got flyers for her basketball camp and all this. And in the flyer she says, I'm better than. Well, she's not going to say she's better than you. No, in her flyer she's going to say, I'm better than Dylan. But she better not say that unless she proves it. So we want proof. So you know what we're going to go for? We're going to go for the jugular here. You better really be better than Dylan. Because she wants to put that in her advertising and all that kind of stuff. Because she's going to get thousands of kids coming to her basketball camp to learn how to properly shoot free throws, with your eyes closed, all that kind of stuff. So now what's going to cause rejection? First of all, one tail or two tail? One tail. I have one tail, 1%. If Z star bigger or smaller, first of all? Bigger. She's got to be extreme in that direction. Bigger than what number?
2.326.
Beautiful. Beautiful. By the way, many of you are still using 2 decimal places. That's incorrect. The only number that's 2 is 196, and it's technically 1960. Yeah, but nobody rounds this is called a critical value. Nobody rounds this. This is not done in real life, ever. Yeah, some of you are getting your information off the computer, and the website you're using is seriously flawed because a lot of you guys are going to the computer, which first of all, you can't do. It's called cheating. It says right on every quiz. Do not be using a computer to do this at all. You're not going to do it on a test or a quiz. But as a result of using the computer, I'm getting incorrect conclusions and incorrect calculations and incorrect comparisons because you're not using the correct numbers. These are constants. You don't calculate these. These are actually constants. Pi, 3.14, blah, blah. That's a constant. You can't change the value. You can report as many decimals as you want. This is the only number used in this scenario. It's always a 3 decimal place value that's used because it's computer generated. You couldn't calculate this if your life depended on it. This requires like graduate level math skill and computer programming at the same time. Somebody did it for you. You don't have to calculate it, but it's a constant, right? So don't change that. It'd be sort of like saying I want to find the area of a circle. And so rather than use the pi key on my calculator, I'm going to round pi to 3. My answers aren't going to be very accurate, are they? But if I use the pi key on my calculator, then the result, I can give you as many decimals as I want because I'm using the correct number to begin with. The only part of the process you round is that one, because that's the only calculation you're doing. Do you notice? I didn't round this because this is 0.83333 forever. I didn't write the decimal. I wrote the fraction. But because these were terminating decimals, I could write them. What if these were not terminating decimals? Then we use these. That's the way it always is. Because you don't want to make the mistake of rounding. Well, why? Because what if it's a close call? And you rounded, so your last decimal place is off by a little, but it was that close of a decision. Ooh, right? Yeah, that would be bad if we went the wrong direction. So now we had them go out and shoot. So now not N1 and N2. This will be N Miskey and Dillon. Okay, so Miskey went out and she shot, let's say, 87 free throws and made 78 of them. Dillon went out and shot 102 free throws and he made 74. So now I'm not using friendly numbers anymore, am I? Ugh, I'm using icky numbers. Why didn't you both just shoot exactly 100? Well, you know, somebody else had to use the court. They kicked you off after 87, and Dillon lost count. He was going to stop at 100, but he was feeling so good, he goes, I'll just get a couple more. This is actually more realistic, that you didn't have perfect numbers. We prefer perfect numbers, but in real life, you don't really have that opportunity. Okay, so what is Miskey's observed value, her experimental probability? 78 over 87. It's not going to be a terminating decimal, so I'm just going to leave it like that. What is Dillon's? 74 over 102. And now, what is their pooled probability? It will be 78 plus 74 over 87 plus 102. How many free throws were made? How many free throws were attempted? You do not add percentages, and you do not average percentages because they have different denominators. So again, these are called weighted averages in general. So what is my numerator? 152. What's my denominator? 189. So therefore, what is Q bar? Well, this is easy. They got to add to 1. 152 free throws were made. How many were missed? 37. Can everybody see that? 37 were missed, so Q bar is 37 over 189. And I need that in my calculation. Those numbers go right here. We now have everything necessary to do the calculation. But this time, instead of putting decimals, I'm going to leave the fractions because these are not terminating decimals. The other thing is, if I convert these to decimals, that's way too much entering them in. It's actually more work. That's not going to make my life easier. So the observed difference is 78 over 87 minus 74 over 102. The hypothesized difference again, 0. That's why I have to have it not as an inequality, but as an inequality of a number. So 0. She says she's better, so we start by saying she's not, meaning no difference. That's why it's a 0. The difference between their skill is 0. My denominator then, I have 152 over 189 times 37 over 189. And then over here, 152 over 189 times 37 over 189. My first denominator is going to be an 87. My second denominator is going to be a 102. So, just like before, big parenthesis, you don't need any more in between. All right, so let's all try this one. This is a little bit busier than the other one. So tell me when you get about it. This one is, go slow. There's a lot of buttons to push. Another thing that drives me crazy about this calculator is the arrows.
These ones?
Yeah. All the arrows, there's something, I always feel like there's something that can go wrong. Does anybody have a number yet? Well, it shouldn't, because it's under a square root, it shouldn't be leaving your answer as a fraction. Is it giving you square root of a fraction?
I got 2.94.
Now, is that, you got 294?
2.94.
That's really close. I have 2.95. Does anybody else have this? We really should have exactly the same number. I'm waiting for somebody else. I have 2.954. Is that what you have? Or do you have actually 2.94?
2.943.
Well, we have one different number then. Waiting for someone. Rashad, you don't have a number yet?
I messed up. That was way off.
Because it really doesn't take this long.
I have a 2.95.
295. So I have the same thing regarding you. I don't know how you could be that close if you have a misentry. What it probably is, Ricardo, you probably have literally one of your numbers is one digit off. And that's it. That's probably what it is.
Yeah.
Did anybody else get 295? We really want to be able to do that.
Yeah, I got 2.95.
Okay, I'm feeling really good about that number. Now, what does this mean? What was our line in the sand, by the way? This is always a good thing to do about right now, and this is bigger than 2.326. Now, I haven't drawn the picture for this problem yet. We were going to reject at 2.326. What was our outcome? Our outcome was here. Are we in the shark-infested lava? Oh, yes, we are. No question we are in the shark-infested lava. So, by the way, when you're in the shark-infested lava, does that make the conclusion easier or harder in general?
Easier?
Easier. When you fail to reject, then you have to figure out what are you going to say is the truth. Is it not enough evidence? Is it that I actually believe the null is true? There's some gray area there. I did not find you guilty. Do I declare you're innocent, or there just wasn't enough evidence to find you guilty? That's kind of gray. But if I find you guilty, it's easy. You're done. You're guilty. We're in the shark-infested lava. So what's my conclusion? Reject the null hypothesis. By the way, that means the alternative is the truth. And what is the alternative in words? What is the alternative in words? In words, what's the alternative?
Whiskey is a better.
Whiskey is a better fruit. Sorry, Dylan. Bad day. You should drink, more coffee before you started. I don't know. Reject the null. Whiskey is a better free throw shooter. Now, it's a good thing because she's already got all the free throw. There we go. And when we say better, we mean it's statistically significant. There is more than just like, she made one more than you. No, this is definitely better. Okay? Okay, this is how it works. Now, let's look at p-values. Because again, to me, p-value lends certainty to this result. Yes, we rejected the null. Is it possible we got it wrong? Is that always, there's always a possibility. In other words, you just had a really bad day. You literally, you had a rotten cold when you were shooting. Or when she was shooting in the indoor gym, you were on the outdoor court and it was raining. Is it possible we got it wrong? By the way, our conclusion is absolutely correct based on the evidence. But is it possible that she's not a better free throw shooter? That we just have a really bad sample? Yes. In fact, in general, how likely are you to get any conclusion wrong in general? Exactly this. It means you can actually get it wrong 1% of the time because there could be just a really bad day. That's why we want that alpha to be small, because we want to eliminate the possibility that we got it wrong. So here's the thing. Let me erase this. The p-value, again, this should make it a little easier to interpret. The p-value here is what is the probability of a result this extreme or more if the null were true. If Miski is not better, if Miski actually is the same level as Dylan, exactly the same level, then what is the probability of a result this extreme? So what is the probability that a z-value could actually be more extreme than 2.95? In other words, I'm asking, what is the tail probability? What is the tail probability associated with this result? Not with my line in the sand, no, with the actual result. So go to your C table. So this is going to be 1 minus what number? So find the probability of being less than 0.295 and subtract that from 1. What am I subtracting? 9984. So this is 0016. If Miski truly is not better than Dylan, if there really is no difference, then we can expect results this extreme or more this often. That's 1/10 of 1%. This should make you feel very confident that no, she's better. That's extreme, right? By the way, shooting. If I said, what's the probability of? I have a fair coin and I want to shoot 10 consecutive tails. You'd say that's really unlikely, but not absolutely impossible. That's on the order of that kind of probability. That'd be like saying a fair coin was tails 10 times in a row. It's not impossible, but it's very unlikely. So we did a test. We have a conclusion. We have to say this. What if we're still not convinced? We don't believe it. Can we test again? Yeah, we can test again. Do we ever test again? I thought if somebody is found not guilty, you don't test them again. But what if somebody's found guilty? Can we retry them? Can we retry somebody who's been found guilty? Yeah, you hear about things every now and then. It's these great heartwarming stories about the person that was in prison for 30 years and new evidence came in and then they exonerated them. I mean, it's horrific that somebody was sitting in prison for years and years and years, but it's always awesome when you find out they've been released. Everybody understand? There was a movie that came out, God, I cannot remember. Michael Jordan, he plays a lawyer.
Just Mercy. Just Mercy.
Just Mercy. Has anybody seen that movie? Oh, it's unbelievable. He's a lawyer in the Deep South, and he's fighting for one particular, I think it's Jamie Foxx is the character. He's been in prison for years and years and years for the crime he didn't commit. And this guy just made it his mission, and it took 4 years. I don't know what year it's supposed to be. I want to say it's the 90s maybe it's supposed to be. And they won. They got free. And because of that, this guy made this his mission in life. This is based on a true story. This guy is still around, and he's still doing this. He's been going after people, not trying to release prisoners from prison. No, people who were unfairly convicted based on, in other words, the term they often use, they were railroaded. They didn't have proper representation and they were sent to prison for life for crimes they didn't commit, kind of stuff. And it's just such a cool story. But it's taking something, we found you guilty, you're done, you're guilty. But the thing is, could we have gotten it wrong? Because we say beyond reasonable doubt, but could we still have gotten it wrong? Well, I mean, how many people go to prison each year? I mean, a lot. How many people are in prison? A lot. If 1 in 1,000 was a mistake, that's a really small probability. But would you agree that's still too many? Yeah. And so the idea is everything we did was correct. That was the absolutely correct conclusion. Is it still possible mathematically, though, that it's the wrong conclusion is what I'm saying. Not that we didn't make a mistake. We did not make a mistake. But based on everything else, is it possible that it really, that's not the case, that there really wasn't a difference? That was just a really bad sample. And I'll go back to the example. We're trying to find the average height of a Mesa College student, and you not accidentally, your random sample happens to have a 7-footer. Is our result going to be a little bit off? Yeah. You didn't do anything wrong. You just had the weird, odd sample that was a bad sample. You didn't do anything wrong, but you have a bad sample. In this case here, if there was really no difference, we have a bad sample, Dylan had an off day. Or we find out later Misty was actually playing on a 6-foot court. No. The short basket. Well, no. So this is how you do it, and you have to trust your results. Now, this is a problem in general. When we are comparing two things, we have to have numbers. The more complicated problem, we're not going to do this problem, but the more complicated problem would be something like, I believe the probability of success in this scenario is this much better than the probability of success in this scenario, a realistic situation. So, for example, I've got Steph Curry over here, and I've got, Shaq over here, and we're going to do free throws. We're not doing a test to see if there's a difference, are we? I mean, Steph Curry, greatest free throw shooter of all time. Shaq, well, not. You might be saying, based on what I've seen, I think Steph's about a 40% better than Shaq. And so I believe that Steph is going to about 40% better. Why is that important? Because now that means that our hypothesized difference isn't 0, it's 0.4. Oh, and therefore what's going to show up right here? A 0.4. If there's situations where you truly believe there is a difference and you have a number in mind that you believe it is. It's that simple. Okay? I have a weighted coin. And I do this all the time. I believe this weighted coin lands tails about 40% of the time, or at least when I do it versus Ava's coin, so I can say, I believe there's a difference of this much. And then you can start the problem that way. If you don't believe two things are the same, you don't start by hypothesizing the difference is 0. Again, think Steph Curry versus Shaq. Nobody believes the difference is 0, and that would be a silly comparison. But you'd say, there's a number that I believe is the difference, and now I'm going to do my comparison based on that number. Everybody cool? So most of the time, most of the time, we're looking at a 0 difference. Okay, and that's the main thing. So now I'm comparing probabilities of success. It could be the same person or the same 2 different instances, or in this case, just 2 different people. It doesn't matter which one it is. I do the problem the same way. This is exactly what we did before. What I observe, but the difference is the pooled probability. Okay, so next time when we do stuff involving mu, we're going to do the same thing. We're going to pool our averages together. Okay? All right, can we go ahead and stop the record? I didn't hear a